proteins. And when you deal with alternative splicing, remember that one gene could result in one transcript that could be spliced alternatively to yield many different types of transcripts, all of which could be translated to get you a variety of different proteins. And again, that tells you some of the complexity that you see in higher eukaryotes. In the initiation of translation is the focus of today, and initiation is rate limiting compared to typical translation elongation, meaning the faster you initiate translation, the faster and more proteins that you can generate. So we've decided, that is Eric and I have decided, that we're only going to teach you a few things about how we get it started, how we finish it, and how we can check for errors. Don't leave this room thinking that this is all of the details that are available. These are all the details that we're going to examine you on. And if you read your textbook, there are copious additional examples of how this all works. But if we're going to worry about initiation, we have to worry about the fact that the two life forms that you guys deal with, eukaryotes and bacteria, do it decidedly differently. And so you're going to be typically questions about how one does it, and more importantly, how that contrasts with how the other domain does it. So typically you want to find a direct open reading frame for your protein, one, because you want to make the correct protein that you're doing, and two, if you start out of frame, you're more often than not going to run into an out of frame nonsense codon producing a rather small polypeptide. There's a reasonable chance that if you find any three nucleotides, and you can calculate this chance, what it will be of being a stop codon, and it's high enough that you want to make sure you start in the right reading frame. So in both domains, in both eukaryotes and in bacteria, translation will always initiate at an AUG start codon. And for those of you who have already memorized the genetic code, which I suggest you don't do until you become a hardcore nerd, that is always going to specify for methionine. And it turns out that if you think about how a ribosome works, normally a ribosome is functioning with one tRNA that's amino-acylated in the A site and one amino-acylated tRNA, which typically has a peptide on it in the P site. Hence, it's why it's named a P site. When you get started, of course, you need to bring in two amino-acylated tRNAs. And of course, how do you fit one into the P site? The way you do that is use a special initiator, methionine tRNA. So there are actually two classes of tRNAs that can encode methionine. One is used at the beginning and only at the beginning of protein synthesis. One is used for all other methionines that must be put in. This special initiator tRNAs, I'll show you some pretty pictures in a second, doesn't have an affinity for the A site of the ribosome, but it does have an affinity for the P site of the ribosome. And we'll go through some of the mechanics of how this works in pretty picture mode. First thing you should realize, we're going to start with some chemistry, and we're going to start in bacteria. The structure in green up there is basic chlorine methionine. Normally, at the very top of the structure, and I'll use the pointer so you make sure you get it correct, all amino acids have an amino terminal end, something called an alpha carbon, and a carboxy terminal end. Then they all have a side chain that comes off them. Methionine side chain is two methylene groups, a thiol linkage to a methylene. You don't really need to know that. But normally speaking, the amino end and the carboxy end are where all the linkages happen. So you generally don't see modifications on those positions because those modifications could only be possible at the very, very beginning of a protein or the very end of a protein. Luckily, in this case, we're talking about the very, very beginning, the true amino terminus of a protein. And in bacteria, the amino acid that is actually carried on the special initiator tRNA is N-formal methionine, where the amino end has this formal group put on it, the formic acid-like group put on it. So again, there are two tRNAs. There is a tRNA F-met and a tRNA M-met, and that's how they're referred to if you're talking about them around the lab. The F-met stands for formal methionine, and the tRNA that's charged with N-formal methionine is exclusively used for translation initiation. All other methionines that might be encoded within the protein use the basic boring tRNA M, which just puts in regular old methionine. And so N-formal methionine can only be found at the N terminus of a protein. If you think about the chemistry of peptide bond formation, you realize that you can't actually form a peptide bond when your amino group has been modified with this formal group. That's what happens in bacteria. In eukaryotes, in you will put methionine at the beginning of every protein. You will use a special tRNA to do that, but that tRNA will be charged with basic boring old methionine. So you have a tRNA that is used for initiation, tRNA met, that is used in eukaryotes. That all making sense? I know it sounds like a lot, but it's really not that fancy. There's a special tRNA that you have to use to get the party started. Both eukaryotes and bacteria do that. In eukaryotes, you charge it with boring methionine. In bacteria, you charge it with a special methionine. So there is, in fact, a special aminoacyl tRNA synthetase that is responsible for charging the initiating tRNAs. The other major difference that we're going to focus on for this class between eukaryotes and bacteria is that a eukaryotic RNA, well, however it is ending up being spliced, is typically only going to encode one polypeptide, whereas many bacterial RNAs are deemed polycistronic. I'm sure Eric Ross went over this with you, where multiple open reading frames can be present on a single RNA.